Hello, my name is Rob Reynolds. Welcome to Calculus section 4.3. Today we're going to look at finding the derivative and analyzing functions so that we can look at the first derivative and tells what it tells us about the graph, second derivative, what it tells us about the graph. So we're going to be analyzing functions. And again, I think this chart is very helpful to be finding inflection points and maxes and mins, intervals of increase and decrease, and identifying concavity. We're even going to start talking about ending behavior asymptotes, or the horizontal asymptotes, and x-intercepts, of course, which we found in Algebra 2. But I'd like to back up. Remember, the goal moving forward is to fill out this big chart. Tell me the first derivative, tell me the second derivative. But I'd like to back up and begin this video by just a quick review. In section 4.1, we were finding absolute values, and the test was just a little bit different. The test for absolutes, you literally just take the derivative, set it equal to 0, find those critical values. And remember, critical values were defined where not only was the function equal to 0, but also if the function is undefined anywhere. That's also critical. And there's nothing undefined, because x squared plus 1 quantity squared is never undefined for any values. You could never set that equal to 0 and you divide by 0. So the only critical value that I see is 1. And then so you'd throw a test in section 4.1. And not only would you use that critical value, you would also use any endpoints. So 0 is an endpoint and 2 is an endpoint. And then you would literally just evaluate the function at 0, 1, and 2. Look at those y values, and the highest number is the max, and the lowest number between 0 and 0.4 is the min. And it's the absolute. There's no relative. So when you started talking about relative mins, that's section 4.2. And you did the same thing. You found the derivative, you set it equal to 0, you found your critical values, and then we started using this chart. And you started saying, okay, well, here's the intervals, and then let's run our test. So our test here looks a little bit different. And to demonstrate that you're actually doing the test and not just cheating and using your graphing calculator to tell me when things are increasing or decreasing, you could show me just a little bit more. Like, don't just tell me f prime is less than 0. You could find that out on your calculator. Instead, your test would look like, tell me what number you're going to plug in there between negative infinity and negative 2, such as maybe negative 3. And then plug that into the first derivative, maybe right here. So if I plug in a negative 3 into this guy, this becomes positive. This becomes negative. Positive times negative, all divided by, well, anything that's squared is positive. And that's why it's less than 0. So this step is really crucial to me when you're taking your quiz and or your test, to show me that blue dot so that I know that you're actually taking the critical values and plugging those into the first derivative to determine whether this is greater than or less than. If you don't show me that work, again, I'm going to assume that you're cheating and you won't get full credit. Then you find intervals of increase and decrease, and when you go from decrease to increase, you have a minimum, and when you go from increase to decrease, you found a maximum. So that's 4.2, and that's relative maxes and mins. Now at the end of 4.2, I ran out of time on the video, and there's something called the second derivative test. And you may think the second derivative test has to do with concavity, but it doesn't. Now, in section 4.2, I talked about concavity, and to find out if something is concave up or concave down, which I think I started talking about a cup and a gown. So if it's concave up, looking like a cup, then the second derivative is greater than 0. But if it's concave down, like a gown, like a lady's gown, then it's the second derivative is less than 0. But that's not the second derivative test. Although the second derivative tells you about concavity, that's not called the second derivative test. The second derivative test actually finds, same as the first derivative test, maxes and mins, local extremes, relative maxes, relative mins. That's what the second derivative test tells you. The exact same thing that the first derivative test tells you. You just do the test a little bit differently. So don't get this second derivative test mixed up with what the second derivative tells me about concavity. Concave up, concave down. So let me talk to you real briefly about the second derivative test. The second derivative test says, take the critical values from the first derivative, plug those into the second derivative and then talk to me about concavity, because if it's concave up, then you've located a minimum at that critical value, which is the max or min. And if it's concave down, then you've located a maximum. That's the second derivative test. Find the critical values from the first derivative and plug them into the second. Let me show you. Here comes the critical values. Well, before you could find the critical values, we need to take the derivative. Then you can factor out a 12, x cubed minus x squared minus, I think this is a 1, so let's just call that x plus 1. And then you can factor this by grouping. Let's pull out an x squared, x minus 1. This turns out to be minus 1, and x minus 1, I worked this out, I believe, in section 4.2. So go back if you don't know how to factor that by grouping. So I think the critical values here turned out to be plus or minus 1. So the second derivative test tells me to take those critical values, positive 1 and negative 1, and throw those into the second derivative. So let's go ahead and find that second derivative. I'll get rid of this example for you because I don't want you to think I'm doing part B. So we'll get rid of that. So here comes the second derivative. It's the derivative of this. 6x squared minus 24x minus 12. We'll factor out a 12 and get 3x squared minus 2x minus 1, which I think this factors nicely to 3x plus 1 and x minus 1. So the second derivative test, again, says take the critical values. We're going to take the critical value one at a time here. We'll take the critical value of a 1 and plug that into the second derivative. If that second derivative is greater than 0, then it's concave up. And if it's concave up, you've located a minimum at that second derivative. So I was just guessing. Let's find out what it is. So plug in a 1. And again, this is where you need to kind of show me. You could tell me the 12 is positive, or you could just throw, well, I'll keep it the 12. But that's not the important part. This is the important part. If I throw a 1 in this one, it's positive. If I throw a 1 in here, or up row, that's 0. So this is really inconclusive. There's no inconclusive. We can't make any determinations from that. I'm kind of glad that happened, just so you can see that it does happen. Let's check negative 1, and let's see what's happened. Let's still get positive 12. This is going to be a negative number. Negative 1 minus 1 is also negative 1. That's greater than 0. There it is. If it's greater than 0, then it's concave up. And then we've located a minimum at this negative 1 comma, and then I have to go back to the function and find the y value at negative 1. That's the second derivative test, and it's possible to have an inconclusive. We don't know what's happening at that point. We'll have to look at the other pieces of the chart. That's why there's big decisions to be made about what's happening at 1, but we can be sure that there's a minimum at negative 1 by the second derivative test. So let's move on for today's lesson. Moving back forward here to 4.3, where they're starting out with a warm-up problem, so something that you should probably already know, that if the first derivative is less than 0, then it's decreasing, and if the second derivative is greater than 0, then it's concave up. So they want to see if you can draw me a decreasing function that's concave up, and that's going to be the left side of the cup. And then moving on to the next interval between 0 and 1. So here's the 0 to 1 interval. In between this yellow section, I need to know, do you know what this means? Well, if the first derivative is greater than 0, then it's increasing, and the second derivative is still concave up. So that's the right side of the cup. And you continue doing this. Let's see, this is going to be increasing again, but this time this says concave down, and so that's the left side of the down. And so you continue doing this process all the way through, and then you can make some determinations about what this function looks like. the overall graph. And it could look something like this, although you don't really know. It could have been much lower. Perhaps it's down over here or something and much higher. But it has to follow those rules. So again, you'll be following these rules by finding the critical points, concave up and down, if you follow that chart. And that's why I created a chart, so it just makes it easier for you to know all of the pieces that I'm looking for. So example number 2 says this is a deceptive problem, but it's only deceptive because of the way that the book is doing it. I think it will be less deceptive if you use the chart that I've thrown at you. But the reason why it's deceptive is usually when you have a critical value here, or I'll put the critical value here, then the left side is like maybe increasing, and then the right side of that critical value usually alternates to decrease, and then you've located. Well, every once in a while it goes increase, and then it goes to another increase, and then that deceives you into thinking, well, wait a minute, what happened there? So that's what happens with this problem. But again, they're setting you up for failure as far as I'm concerned by doing this number line. You just have to be a little bit more careful than if you're using my chart. So he says use the graphing guidelines. Graphing guidelines, that's not graphing calculator. This is the, tell me all the things you know about this by finding the first derivative, the second derivative, and then talking about intervals of increase and decreases and max and mins from there. So let's go ahead and take the derivative of this. Remember, this is the same thing as 1/3 x cubed. So the derivative of that is really just x squared minus 400. And when I set that equal to 0, I get plus or minus 20. You could use the second derivative test and plug that into the second derivative, just like I did on the last example. But don't use the second derivative unless it specifically asks you to use the second derivative. Let's go find the second derivative, which is 2x. Set that equal to 0 and get x equals 0. You can see why they've chosen negative 20, 0, and 20 to put all of the critical values on the number line. Now, in my chart, I kind of break up the first derivative critical values with the second derivative critical values. I think it makes it a little bit easier. But there's nothing wrong with what the book does. Just be careful. You might get deceived if you do it this book method. So let's go ahead and test something to the left, like negative 30. And you run your test and you find out that this is increasing. I'm skipping some steps just for the sake of the video, which is concave down. And then you would pick some number in between here, like negative 10. Plug that into the, whoops. No, wait. The only reason that you know that it's concave down is by checking the second. I really skipped some stuff. Throw this negative 30 in right there, and because that's less than 0, that's concave down. So throw in a negative 10 to the first derivative, and which is this guy, and this will be still less. Oh no, it'll be less than 0. Yeah, because negative 30 squared, if I plug it in here, negative 30 squared is greater than, it's 900, but this is only 100. So this is going to still be less than 0 or decreasing, and then you'll have to figure out some way to show me that you're actually doing this instead of just cheating on the calculator. And then you would go to your second derivative and plug in the negative 10, and of course that's going to be less than 0, and it's still, look at that, concave down. So what we have here so far on the graph is increasing and concave down. And so that looks like the left side of the gown. And then decreasing and still concave down looks like the right side of the gown. And then you continue this process. But I think what was deceiving was we went from concave down to concave down, and it did not alternate concave down, concave up. So every time it alternates from concave down to concave up, you've actually found a point of inflection. Let me show what I mean. If you pick the first derivative at 10 and plug that into the first derivative, it's still less than 0. It's going to be a negative number, so it's still decreasing. But then the second derivative at 10 is going to be greater than 0, and that's going to be back to concave up. So as soon as you write the words from concave, all of this was concave down, and then you switch to concave up, that means that you have a point of inflection at this guy, that critical value, 0, something, and you would have to go back to the original problem to find out where that point of inflection. And what the heck does a point of inflection look like? Well, it's where concavity is changing. So again, I would recommend that chart. So we know that well, intervals of increase and decrease don't tell me about points of inflection. So there's concave down, and this is concave up. There's your point of inflection. And I'm trying to figure out if there it is. There they've graphed it for you. So there's concave down is on this side, and then over here is concave up, like a cup, and that's called the point of inflection right at 0. And this video is getting a little bit long, but I really wanted to show you a problem by using the chart, because I'm going to be asking for you to use the chart on the test, and I need to show you that example. Again, the book takes a little bit different approach of what their chart looks like, but I'm going to use my chart instead. None of these numbers make sense to you because we haven't found the derivatives yet. So go ahead and spend some time finding the first derivative and the second derivative. That's no easy task, but for the sake of the video, I've worked them out here for you. So here's the first derivative. The second derivative is not easy. I would recommend, instead of multiplying all of this together and then multiplying all this together, it's easier and it's a little bit cleaner. If you can see, this has an x squared minus 1, this has an x squared minus 1. I would look for greatest common factors. A lot of times students don't like doing that, and then they get really bogged down by multiplying all of this out. It's really much faster to pull out a greatest common factor. So there's a 20x, and sure enough, there's also a 20x in this term that you could pull out the GCF. So again, I encourage you to look for the greatest common factor instead of multiplying things out. That should save you time, but no doubt this problem will take you a long time to find the first derivative and the second derivative. But let's suppose that you've done that already. So I've listed here the first derivative and the second derivative. Talk to me about what goes here, and I would list this in factored form. So if 10x squared is a factor, then x equals 0. This gives you x equals plus or minus the square root of 3. And looking at the denominator, you may think x squared minus 1 equals 0 when x equals plus or minus 1. But the original function, I can't let x be 1. So it's outside the domain. It says graph this function on its domain. So I would not list -1 and 1 as critical values because I've got vertical asymptotes at 1 and -1. So maybe you think that they're critical. Vertical asymptotes just mean I'm going to have this guy increase, and usually this guy is going to be decreasing. But some textbooks call -1 critical, some textbooks do not. Maybe for that fact alone that it is going to switch from increase to decrease, maybe and it says find intervals of increase and decrease, let's list it. So we've got a lot here. We've got 0. Let's see, this is -1, so, oh my gosh. Negative square root of 3. Why did I choose this problem? -1 is critical. I'm going to have so many criticals I can't even use my bubbles here. Well, let's put them in order from least to greatest, and maybe it'll fit. Negative square root of 3, -1, almost. 0, 1, and positive square root of 3. So my intervals are going to be from -infinity, negative square root of 3, negative square root of 3, -1. See, you can imagine how long this one problem is going to be on your test, but I will be assessing several things from this one problem. Let's see, this goes from the square root of 3 to infinity. The problem is if you mess up on the first derivative, then your second derivative is going to be wrong, and your whole chart's going to be wrong, and you're going to get 0 points. No. Well, yeah, but be careful on this problem because it's long. For the sake of the video, I think you'll find out this first derivative is greater than 0, which means it's increasing. All of these will be the first derivative is less than 0. That means that it's decreasing, decrease. This guy's decreasing, and then this guy's going to be back to increase. I think I've done it correctly. So that means that you found, if it goes from increase to decrease, the max at negative square root of 3 comma something. We'll use our calculator to determine that. And then here we've located a relative. These are not absolute, but relative means at the positive square root of 3. And the only time that I would recommend that you use your calculator here that I don't need to see your work. So if I hit zoom 6 to give you a standard 10 by 10 by 10, and then zoom 0 will try to fit the graph. And you can see there it is. It's increasing on this interval. decrease, 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 and then back to increase. And so we want to know where are these maxes and mins. So all I have to do is trace at the square root of 3 and find out that it's around 25 point, and you could evaluate and tell me the exact, but I would take the decimal this time, 25.98. And then you could find it at the negative as well. So then go to the second, do the same thing, fill in the chart, talk about concavity. Points of inflection is, again, you can see where your points of inflection are at, and you can see your concavity. So somewhere along the line, you're going to get a concave down. Well, let's see if I can just grab this real quick. There is nothing really quick in calculus, of course. This all takes so much time. And so you can see that right here is concave down. And so just cheating along here for this whole interval here, and that's why my chart's helpful. The interval would actually be for just the second derivative, zeros. Let's see. I think there's a typo in here. I think this should be a minus. We didn't work it out, but I think the author has a wrong thing here because I think we've got zeros plus or minus the square root of 3 still for your critical values. Oh boy. So yeah, they're all in here. This is a massive problem. So in your 8, the video is running long, but I do think you're going to get concave down in this interval. This will be concave up. This will be back to concave down. And then this will all be concave up. And the only way to check that is if your points of inflection is if concavity is changing. So look, concavity is changing. Here's concave down to concave up. But there was no point of inflection. Again, a little bit deceptive because there's a vertical asymptote here at x equals -1. So if you add the vertical asymptotes in, make sure you don't get trapped telling me that there's a inflection there. There is no point of inflection. The only point of inflection that you'll put on this chart is at 0, 0. All right. I hope this video was helpful. I apologize again for the length, but there's plenty of problems for you to go through. Remember, you have worked out solutions posted on Blackboard. Here's the author going through explaining. There's the function that I tried to graph. I should have just gone to this slide. But there's lots more functions. If you don't know how to take the derivative of this, you're sunk. So practice taking the derivative of e to the u. So just a quick reminder, the derivative of e to the u is not e to the u, it's e to the u du. So you might have to do a little let u equal -x squared and go find your du. That's called chain rule. Good luck. And again, I'm not a big fan of this number line. I would practice the chart, and I'll see if I can post a document with lots of charts on it so you can practice that as your leisure, because I'll be asking you to work the chart out on the test. Good luck.